My name's Hailey Banack, and I'm a postdoctoral fellow in epidemiology at the University at Buffalo. I'm here to talk to you today about a paper that's published in Epidemiology called Stratified Probabilistic Bias Analysis for BMI-related Exposure Misclassification in Postmenopausal Women. Body mass index, or BMI, is the most frequently used metric to categorize individuals according to their body weight status. However, despite its really widespread use, there are a number of limitations associated with using BMI. One of the main concerns is that it really doesn't accurately represent an individual's true obesity status, resulting in what we would call exposure misclassification. The objective of this study was to examine and adjust for exposure misclassification bias resulting from using BMI to define obesity in postmenopausal women in the Women's Health Initiative. This manuscript includes results from two distinct analyses. First, a validation study exploring the sensitivity and specificity of obesity classification defined by BMI compared with percent body fat measured by dual energy X-ray absorptiometry, or DEXA scan. And the second analysis was an age and race stratified probabilistic bias analysis to investigate the impact of BMI-related misclassification on the association between obesity and mortality in postmenopausal women. For the validation study, we modeled sensitivity and specificity using logistic regression, and we controlled for important predictors of misclassification, such as smoking status or physical activity level. The results from this validation study indicated that the sensitivity of BMI-defined obesity was higher in non-Hispanic Black women than in non-Hispanic white women across all age categories. There was also a really consistent pattern of decreasing sensitivity across age strata. So what does that mean? The sensitivity of using BMI to define obesity was lower in older women than in younger women. We then used the results of this validation study to conduct a stratified probabilistic bias analysis with Monte Carlo sampling techniques. The bias analysis consisted of three steps. First, we modeled the bias parameters. We then used record level correction to correct for exposure misclassification. The third step was estimating the effect of obesity on mortality using the bias corrected exposure variable. These three steps were then repeated 80,000 times to create a distribution of effect estimates. We then compared the results of the bias-adjusted analysis with the results from a conventional statistical analysis. Comparing results from the conventional analysis and the bias analysis demonstrated that BMI-related exposure misclassification produces a bias towards the null, which led to an underestimate of obesity-related mortality risk in this sample of postmenopausal women. The bias-adjusted estimates were greater than the conventional estimates across all age categories in both Black and white women. These results highlight the importance of using quantitative bias analysis to adjust for BMI-related exposure misclassification. To the best of our knowledge, this is the first study to demonstrate the use of stratified probabilistic bias analysis to account for exposure misclassification when there is potential for effect measure modification.